Hi, in this video I will show you how to use mlpack to do parts of speech tagging using hidden Markov models. So we will be using this dataset. So it is this URL paperswithco.com slash dataset slash treebank. So it is I think Twitter data, or as it is called today, X. So here you can see that it can be used for parts of speech tagging and also for dependency parsing, which is another task in natural language processing. So I will go to the home page here. So it's a GitHub repository, and here we can find these three files. These are co-NLLU format files. So let me just open this file to show you what how this file looks like. So it looks like this, and if you want to know the structure of this file format, then you can go to this link, universaldependencies.org/format, and it has this co-NLU format. So let's go through that. So it has three types of lines. So there are word lines, which contain some different information like the word, the post tag, and so on. Then we have this blank lines, which marks the sentence boundaries. And then we have these lines that start with a hash symbol, which is basically comments. So let's go back to this file here. So we can see that it begins with some comments, and in the comments you can see they have mentioned the sentence, and then we have these word lines which has lots of information. We will see shortly what kind of information is there. And then we have blank lines to separate two sentences. So now let's go back to the format here, and we will see what information these word lines can have. So first is the ID of the word, the index. Then we have the form, which is the actual word. Then the lemma, the stem of the word. Then the parts of speech tag. And then we have other parameters which are used for the dependency parsing task. So what different tags we can have? We can see that in this link. So it mentions the list of all possible tags that we can have. So adjectives, adverbs, nouns, and so on. And for our task of pause tagging, we will only need to know the form, that is the word, and the tag. That's it. We won't need other information here. So we will be using this file, enudtweet_train.conlu. I have already downloaded it locally, and I have saved it in this file, data.txt. These are all the source files that we will require, and we will go through them now. So let's have a look at this file, preprocessconll.cpp, and let's go to main function. So here what we are doing is we are calling this read file function, and we are trying to read this file data.txt, and then we are storing the contents of that file in this variable file contents. Then what we are doing here is we are opening two files for writing, lines with words and lines with tags. So lines with words will store all the words of a sentence, and lines with tags will store all the tags of that sentence. So we are kind of separating the words and tags into two different files. Then what we are doing is we are calling this parse file contents, and we are passing the file contents of this data.txt to that function as argument. So let's have a look at this function. So I will search for parse file contents. Yeah. So basically it accepts the file contents as arguments, and it returns a vector of this line word stacks which is basically a vector of a pair of word and a tag. So we are doing the parsing here as per the CoNLLU format that we discussed. So for example, you can see that for a line which doesn't start with a hashtag, which is for example um, a word line. So for that we are kind of separating the line with this delimiter tab. If you go to this format here, so you can see that the word lines, they are separated by this single tab characters. So basically this block is just parsing the file as per the structure which is mentioned there, and then we get the result as this file, this vector of line word tags. And what we do down here in main is we iterate to this vector. So basically this each element is uh, an entire sentence. So entire list of words and tags of a sentence. That is what this each element of this vector represents. Then we iterate through each pair of lines, words and tags, and we do some pre-processing here. That is, we eliminate certain word tag pairs based on some conditions. For example, if it starts with this RT, so RT in that data set I think refers to reply to. So we don't want that because it will just bring some unnecessary noise. And similarly, we do for other things. For example, if it starts with this user, or if it starts with this colon, ends with this colon. If for example it has this tag emoticon, then we don't want that. So we ignore those word pair tags, and for the rest, we kind of store the entire lowercase word in this file, lines with words, and the tag in this file, lines with tags. And that's it. Like that's what happens in pre-processing. So let's try to compile this file and see what output we get. So we'll use this command. So gtest plus preprocess conl.cpp. Then the output file will be this preprocess and the other flags. Okay. So this exe has been created preprocess. So let's run it and see what output we get. Okay. So it has completed running, and we have got these two files, lines with words and lines with tags. So let's quickly open them and see what contents it has. So lines with words has individual sentences, and you can see these are the words of the sentence, and the words are separated by spaces. Uh, and yeah, that's it. And then let's see what does this lines with tags contain. So it has all the tags of that corresponding sentence in which was there in the lines with words. So these are all the tags of each sentence. So now let's have a look at hmmtrain.cpp. Okay. So what we are doing here is first we are reading unique words from this file lines with word.txt, and we are storing it in this vector unique words, and the same we are doing it with tags as well. So we want to find the unique tags from this file, lines with tags, and we are storing it in unit tags. So now in mlpack, if we want to use hidden Markov models, then it expects the data to be in this format here. So the data or the observations, so they have to be in this format. So it has to be a vector of matrices, and each element of this vector is basically representing a sentence. So this matrix is one sentence. and each column of this matrix is one observation. So if an observation has multiple parameters, then it is represented by this column vector. So in our case, the matrix will, this column vector, it will only contain one row because we only have like one parameter as observation, that is the word of the sentence and nothing else. So this matrix will be basically just a row vector. It will not be an entire matrix, it will just be a row vector. And then for the states, that is the pos tags, we again have a vector of rows, and each row is basically the sequence of states for each sentence. So now what we are doing here is we are first creating an object of HMM. Here we are passing a unit tags dot size, so the total number of states, and then we are mentioning this distribution. We are creating a discrete distribution, and we are passing unique words dot size in the constructor. So this is like I think the number of observations, total number of observations. So now we are reading this file lines with word.txt. We are opening it for reading, and then we are creating this vector of matrices as we discussed before for data sequence. For each line of this file, what we are doing is we want to create a mapping between word and some double value, because this matrix here, it expects values to be of data type double. So we have to create a mapping between word and a double value. So what we are doing is for each word, we are just searching that word in this list of unique words that we created earlier, and we are trying to find the index of that word. And that index, we are adding it to this indices vector, and then we are creating a row vector out of this indices, and we are passing this pushing this row vector in this data sequence matrix. Then we are doing the similar thing for tags. So we are opening lines with tags.txt for reading. We are creating this vector of rows for the state sequence, and then we are reading each line. We are creating this vector tag indices to store again the mapping between tag and its respective index. And each tag, we are searching in this unit tag list and getting its index. So that index, we are adding it to this tag indices, and then we are adding this tag indices vector to the state sequence. So we are basically constructing that structure that we discussed before, and then we are calling HMM.train, wherein we are passing data sequence and state sequence that we created. And after the training completes, we are saving the generated model in this HMM.xml file, and that's it. That's what HMM train does. So let's see what is there in HMM predict.cpp. Okay, so let's start with the main function. So we are creating an object of HMM, and we are loading the model which we created before into that object. Then again here we are creating the list of unique words and unique tags like we did before. Then what I've done here is I am prompting the user to provide a sentence as input. Then I'm breaking the sentence into words, and I'm trying to create the structure of data sequence that I mentioned before. So I'm kind of creating a vector of doubles for storing the indices of each word, and then I'm creating row vector from that vector of doubles, and then finally I'm using this row vector to create this input data matrix. Then I'm creating an empty row vector for storing the predicted states. Then I'm calling HMM.predict, wherein I'm passing the input data matrix that we created before and the empty row vector predicted states for storing the pos tags which it will predict. And the result of this HMM.predict is the log likelihood, which is like how what is the probability log probability of occurrence of that particular state sequence and that sentence. So then I'm just printing out the words and the tags that we got, and also the log likelihood. So that's what HMM predict does. So let's compile these two files. So G++ utils, we have to provide two files here. Utils.cpp contains some important utilities. So utils.cpp, hmmtrain.cpp, and we are storing the output in this HMM train executable and followed by all the other flags. So let's compile. Okay, so it has completed the compilation. So let's run this file, hmmtrain. Okay, so it has completed running and it has generated this model file here, hmm.xml. So let's open it and see what it contains. So it contains a matrix of transition probabilities. So you can see there are 17 rows and 17 columns. So for 17 different states or post stacks. And then we have this data here, which are the probabilities of transition between different states. And then we have initial probabilities here for each of the 17 states. And then below that, we have emission probabilities. So emission probabilities, we have a kind of matrix-like structure wherein we have this top level value. So for example, this is value 0, and there are total 17 such elements. So for 17 states, and for each of these state, we have again, I think, a column vector which has 5,103 rows for those many words. And so that basically means like for each tag, what is the probability that this word will be observed or will be emitted, that is stored in this column vector. So you can see like if we go to the end of the file, you can see it has this value 16. So from 0 to 16, it is 17 values. So that's what this HMM.xml contains. So let's compile hmmpredict.cpp. Okay, so the command is almost the same, only the source file and the executable file name has changed. So let's compile. Okay, so it has compiled. So let's run this. So it is prompting me for a sentence. So let me try to think of a sentence. I know the ball is round and green. Let's see. Okay, so we have got some output. So the is a determiner, ball is a noun, this is the auxiliary verb. Round is a verb, okay, and is a conjunction, and green is a proper noun. So you can see it is making some mistakes here. So round here should be an adjective, and green should also be an adjective. So it is possible sometimes the errors can happen when we don't have the data to support that. Sometimes the words are not present in the word list that we have created. So it is possible that we can get some weird output sometimes. And here also we are printing the log likelihood. So minus 39. So I think the closer this value is to 0, the more likely that sentence uh, can occur. So this is, I think, not bad value. So let's try some other sentence. Let me think. Okay, so I am drinking water from my bottle to satisfy my thirst. Okay, so it has given us the output. I is a pronoun. Okay, am is auxiliary. Drinking, drinking it is showing is wrong because it should be a verb. Water also it is not showing correctly. It should be a noun. From is at position. Mine is a pronoun. Bottle should be a noun. To is at position. Satisfy should be a verb. My is a pronoun, and thirst should also be, I think, a noun. So uh, these tags, which have these words which have these tags punked, I think they are not present in the word list, and that's why it is just throwing some random tags for those words. So that's possible. Uh, and I think we can improve this. So let's see some quick improvements that we can do. The first one is to use a better word list, the one which will have a large number of words. The second one is to do some spelling correction during pre-processing. For example, if some word has incorrect spelling, then we can correct it. Next one is to expand short forms. For example, if it is don't, then we can expand it to do not. The next one is to expand acronyms, abbreviations, and so on. And the last one is during trading and prediction when we are searching for words. If the index which is returned is -1, then what we can do is we can try to find the closest match to that word in the word list and return its index. So if you want a word list, then I suggest you go to this website norveg.com/ngrams, and at the bottom of the page you can find this file here word.list, and it mentions here it has more than 260,000 words. So it should be a good word list. So you can see all these words here listed in lexicographical order. So you can use this list. Also, this link mentions, it provides a link to, for example, if you want to write your own spelling corrector, then you can follow this article here. So it is this article here. So he has shown how to do spell correction using Python, but I think the same you can do it in C++ as well. And I think he has used something called edit distance. So it is also known as this Damero-Levenstein distance algorithm. So you can refer to this algorithm, this Wikipedia page, if you want. So I have uploaded the codes which I showed you in this video in this repository. So you can check it out there. Thank you for watching this video. Hope you found this video informational.